Hello everyone, today I'll talk about the solution of the problem shortest palindrome. We're given a string, we can append letters to the beginning of the string, and we want to add the fewest new letters such that the final string is a palindrome. And if our original string was a palindrome, we don't have to do anything. This problem has two parts. One part is thinking how to transform this short but pretty weird condition into something more natural, and the other is implementation. So we'll start with the idea, and then before implementation I'll talk about the prerequisites there, because this is a string problem, a hard string problem, so without prior knowledge of what you can do with strings, it might be difficult to solve those problems even if you get the right idea. So let's start by thinking about what this operation of adding characters in front of the string actually allows us to do. So let's say that we have some string that's a palindrome, and it's a palindrome when we have added those two letters at the beginning. So at first the string was CBA, and we have added the letters A and B at the beginning, such that the final string becomes a palindrome. Well, it's clear what letters we had to add, because this string is not a palindrome, and this thing that we are given at the beginning, it will be a suffix of the final string. So if the string ends with A, then it will always end with A, so we must add an A at the beginning. And now those A's are satisfied, and then if the string ends with B, we have to add a B at the end. So in essence, that process that adds letters in front of the string is exactly the same as removing letters from the end of the string. So now the question asks us, what is the fewest number of letters that we have to remove from the end of the string, such that the final string is a palindrome. So for instance, for ABA, BC, this is not a palindrome. If we remove C, this is still not a palindrome. If we remove B, this is a palindrome. So the answer is that we have to remove two letters. And indeed, this corresponds to our solution, because we can write the same thing but in reverse in front, and the final string is a palindrome, and we have added only two letters to the front. So this is the main observation. And now what the question is actually asking of us, since we want to remove the minimum suffix, that's what is the longest prefix of the original string, right? Because this thing was added. So what's the longest prefix of the original string? That's a palindrome. And this is the point at which there are some prerequisites. You should know some algorithm that allows us to do basic operation, so something basic on strings in linear time, because we want to solve this problem in linear time. My solution that I'm going to present is based on hashing. While I'm a big fan of string operations and string algorithms, I like algorithms such as KMP and its modifications. And of course, there's also the Mannakers algorithm for palindromes. I'll talk about them at the end, but hashing is typically preferable because when you can use hashing, it's typically the easiest solution, because what hashing essentially allows us to do in its basic form is to compare, after some precalculations, to compare strings in constant time. So compare any two substrings of the same or different strings in constant time, which is a very powerful tool, and it's pretty easy to implement it, and it's very easy to understand actually why it works. And it also has the benefit that it can solve problems like string matching, it can solve other types of string problems, and typically a wider array than any single algorithm. And also there are some problems, including problems not related to strings, that can essentially only be solved with hashing, where the model solution will use hashing, and there is no simple typical algorithm that solves this problem in the same complexity. So in our case, essentially what we want to do is we want to find the longest prefix that's a palindrome. So that means that, again, we have this ABABC, the longest prefix, such that when we reverse the string CBABA, the suffix of the string is the same as our prefix. Because that's what you get by reversing a string. When you reverse a string, then any prefix turns into a suffix, and if we want that prefix to be a palindrome, so read the same from the front and from the back, then this suffix has to be exactly equal to this prefix. So we can do it using hashing in a very simple way, because we can just calculate the hash for the first, so for the starting string and the reverse of that string, and try to compare the prefixes of all the lengths with the suffixes of the same length and get the biggest one, and this is our result. Now, of course, since there is this nice formulation about this prefix being equal to this suffix, this allows us to easily use algorithms like KMP that are based on strings that are both prefixes and suffixes of some string, of some prefix of a string. So you can just concatenate those two strings together and run KMP on that. But here in hashing we don't have to actually think about this. We just want to know what substrings to compare. We have to compare the given prefix with the given suffix. Specifically, we want to compare for length, for a given length, the prefix, so from 0 to L not included, the substring of the original string, with the substring of the reverse string, ending at the end of that string, starting length steps before. So this is the basic comparison that we're going to be using. Now here is the implementation of the hashing class. We'll get back to it. And the algorithm, assuming we have hashing that allows us to compare substrings of the two given strings, is very simple. At first we just look at the edge case where S, but it's not really an edge case, it's just a starting point where S is an empty string, you can just return S. It's not necessary depending on how you implement it. In this case it was convenient. And also a helper function which takes a character and tells us which character it is in order starting from lowercase a. So a is 0, b is 1, and so on. We do it using the ORD function in Python, which gives us the ASCII value of the given character. So by subtracting the ASCII value of our current character, and from that subtracting the ASCII value of a, we get exactly the offset from a, so the position in the alphabet starting from 0. So we get our string, we reverse it using the standard Python slice notation. This is the notation for reversal. This is the reverse string. We calculate the hash for the string forward, the string backwards. We have to make sure that those hashes use the same base and the same modulus, because we want the values to be equal at different substrings. And now we go through all the lengths, starting from the biggest length, so from the whole string. We compare the prefix with the suffix. If we have found a match, then we break. And then L is the biggest, the length of the longest prefix, that's also a suffix of the reverse string. So we can just take what remains after L, so S, and what this slice notation tells us, everything from L forward. We can reverse it, append it to the original string, and this is the string after adding the fewest letters to the beginning. That creates a palindrome. And so here we have used hashing as a black box, and if you know how to implement that black box, then this is the whole solution. For those who are not that familiar with hashing, the idea of hashing, of course, is that we're going to be looking at a string essentially as a polynomial, so as something of a form a plus, so let's a0 plus a1 times base to the power of 1 plus a2 plus base to the power of 2, and so on. And now those a's are going to be our characters. So that means that this is the first character plus the second character times this special number base plus the third character times base to base squared. And this should be, of course, times. And this is some single integer value. And what hashing allows us to do is to, when we have calculated, for instance, the value for every prefix, to calculate a value for every substring. This is called Horner's schema, the idea of that. And that's because if we have something like, so this is what I've written here. So this is the same thing as a0 plus b times, because everything here is multiplied by b at least once. This is a1 plus, and this is b times a2 plus, and so on. So this allows us to look at a different way at our hash, right? So this is a different perspective. And this perspective means that we can calculate the hash of any substring from the hash of the prefix up to its end and the prefix up to before its beginning. We'll see the specific way of doing that in code because it's very simple. So, assuming that we have the hashes calculated, so the hashes of every prefix, and we want to calculate from start to end the hash of the given substring, then we first take the hash of the whole prefix up to the end, then we subtract the letters we don't want, so the hash up to before the start of what we want, because our hash table is offset by 1, it starts with the hash of the empty prefix. And we have to multiply it by the appropriate power of our base. So this multiplication by the power is essentially similar to, you may think of, instead of dividing, which would be difficult, to reduce the, because of course on the, if we have the suffix, then on that suffix we have some big powers of our base. Instead of dividing by that power, we can multiply the prefix by that power. So feel free to read up about hashing or try to understand the process yourself, but the final here expression is pretty simple. And now, of course, to calculate the hashes, we can do it in the standard prefix fashion. So we start with the hash of the empty prefix, which is 0, and every subsequent letter, we take it, we add it to the prefix that we have had calculated previously, but that prefix we multiply by the base. And of course, at every step we have to take modulo. We also maintain a list of consecutive powers of the base, modulo our modulus, and that's also the standard prefix calculation. We start with 1, and then we take the previous one, multiply it by the base, and so on. The base in this case is just a random number up to the module. Of course, also a note about hashing. You can use multiple hashing, so with multiple, let's say, random bases, and that might be better if you have some adversarial examples, or if you just want to be sure, because hashing is inherently a probabilistic algorithm. That's because the number of possible strings is much greater than the number of possible integers from 0 up to the modulus. So there will have to be collisions among all the possible strings that you'll get. And the more strings you get, the more collisions you can expect.